The universe is a silent ocean of darkness, but it may not be empty. We are about to map 10 cosmic addresses where alien life could be hiding. By the end, you will see the cosmos not as a void, but as a frontier teeming with possibility. We will journey from hidden oceans beneath alien ice to atmospheres where life might float on acidic clouds. What if everything we think we know about biology is just one chapter in a much larger story? How does it feel to consider that we might not be the only ones looking up at the stars? A cracked, pale sphere hangs against the blackness, etched with lines of rust red like ancient scars. This is Europa, one of Jupiter's many moons, and its fractured, icy face is a frozen mask hiding one of the solar system's greatest secrets. Beneath an ice shell many miles thick churns a global ocean of liquid water, an alien sea containing perhaps twice the volume of all the water on Earth. It is a world entirely encased, a water world locked in ice, kept from freezing solid not by a distant sun, but by the relentless gravitational embrace of Jupiter itself. The giant planet's pull squeezes and flexes Europa's core, generating enough internal heat to maintain this vast, dark ocean. And where there is liquid water, warmth, and the right chemistry, the possibility of life begins to whisper. For decades, this moon has captivated scientists. Researchers like NASA Dr. Robert Pappalardo point to the reddish-brown material streaking its surface, possibly salts and organic compounds welling up from the ocean below, painting clues on the ice. The real hope, however, lies in the unseen seafloor. Just as on Earth, where hydrothermal vents on the ocean floor create oases of life in total darkness, Europa could host similar systems. There, in the perpetual night, life would not rely on sunlight, but on chemosynthesis, drawing energy from chemical reactions between seawater and hot rock. Entire ecosystems of bizarre organisms could thrive in the warmth of those vents, completely independent of the sun, defining a form of life as we don't know it. To solve this mystery, NASA is preparing the Europa Clipper mission, a spacecraft designed to make dozens of close flybys. It will not land, but it will use a powerful suite of instruments to peer through the ice, analyze the composition of surface materials, and most tantalizingly, sample plumes of water vapor that may occasionally erupt into space from cracks in the shell. Each pass will be a careful search for the chemical signatures of biological activity, for the building blocks of life suspended in those fleeting geysers. The quest for Europa is a quest to open a locked door, to glimpse into an abyssal world that has been isolated for billions of years, a hidden ocean that may hold our first answer to the profound question of whether we are alone. And as we turn from this icy vault, we find another moon where the ocean is not hiding, but actively shouting into the void. From a hidden ocean locked in ice, we arrive at a world that is actively spraying its secrets into space. Enceladus, a small, gleaming moon of Saturn, is not a silent vault like Europa. It is a cosmic fountain. The Cassini spacecraft did not just observe this moon from a distance. It flew directly through shimmering plumes of water ice erupting from its south pole, tasting the spray of a global ocean that lies just beneath a thin, icy crust. This was not a gentle leak, but a powerful, continuous cryovolcanic eruption, a geyser on a planetary scale. The data sent back was breathtaking. Within those glittering jets, Cassini found simple organic molecules, the carbon-based building blocks of life. It detected salts like those found in Earth's oceans, and perhaps most tellingly, it found tiny particles of silica, a mineral that on Earth forms only in very specific conditions, specifically in hot water interacting with rock. For researchers like Dr. Carolyn Porco, who led the imaging team, this was a revelation. Those silica nanoparticles were a virtual fingerprint, pointing to hydrothermal vents on the seafloor of Enceladus, where hot, mineral-rich water from a warm core mixes with the cold ocean above. This tiny, 500-mile-wide moon was suddenly transformed. It was no longer just a frozen ball of ice. It had all the ingredients for life as we understand it, a global ocean in direct contact with a warm, rocky core, providing liquid water, chemistry, and an energy source. The environment within those dark, deep waters could be strikingly similar to the hydrothermal vent ecosystems on Earth, places teeming with life that needs no sunlight. The beauty of Enceladus is its generosity. Unlike Europa, where we must work to peer through miles of ice, Enceladus delivers samples of its ocean directly into space. Future mission concepts now dream of sending a probe to fly through these plumes again, but this time with instruments sensitive enough to look for more complex organic molecules, like amino acids, or even to detect the chemical imbalance that would scream of biological activity. Some daring proposals even aim to look for the husks of cells frozen in the ice crystals. Enceladus presents us with a profound idea that a habitable world does not need a sun-warmed surface. It can be a small, icy moon kept warm from within, offering its potential for life not on the ground, but in the deep, dark water, and occasionally throwing that possibility up into the starlight for anyone passing by to see. This shifts our perspective entirely, from searching for Earth-like surfaces to considering environments where life, if it exists, might float not in an ocean but in an alien sky. The surface of Venus is a crushing, scorching vision of planetary extremes, where temperatures soar high enough to melt lead, and the air pressure feels like being a kilometer deep in an ocean. It is, by every measure, a place where life as we know it could never take root. But lift your gaze 50 kilometers up into the thick, perpetual cloud cover, and the story changes dramatically. In that specific band of Venus's atmosphere, the pressure eases to nearly what we experience at sea level on Earth, and the temperature settles into a remarkably comfortable shirt-sleeve range. It is, paradoxically, the most Earth-like environment in the entire solar system, and it floats permanently in the acidic sky of our closest planetary neighbor. For decades, astronomers have observed mysterious, dark patches drifting through these sulfuric acid clouds, patches that absorb ultraviolet light in a peculiar way no known Venusian chemistry can fully explain. This anomaly has led scientists like Dr. Sarah Seeger at MIT to propose a radical idea. What if these patches are not just strange chemistry, but a form of aerial biology? In this model, microbial life could exist not on a surface, but suspended within the cloud droplets themselves. These hypothetical microbes might use the faint sunlight filtering through the haze for energy, a process called phototrophy, and could even have a life cycle that involves falling into the lower, hotter atmosphere in a dormant, spore-like state, only to be lifted back up by atmospheric currents to reactivate. This concept of a sky-born biosphere completely upends our traditional search for life. It challenges the foundational rule to simply follow the liquid water, because here the solvent is not water but sulfuric acid, and the habitat is not a planet but a permanent cloud deck. To investigate this breathtaking possibility, new missions are being prepared. NASA's DAVINC mission will send a descent probe through the atmosphere, analyzing its composition in exquisite detail as it falls, sniffing for complex molecules that might hint at organic processes. The VERITAS orbiter will map the planet's surface geology from above, helping scientists understand if volcanic activity could be supplying nutrients to the atmosphere that could sustain such an ecosystem. The search on Venus is a search for life in a place we never thought to look. expanding the very definition of a habitable zone from a planet's surface to its skies. It forces us to consider that life may not need a welcoming world beneath its feet, but might instead find a way to float, forever adrift in a temperate, alien haze. And if life can carve out a niche in the acidic clouds of a hellish world, then it truly could be anywhere, even on small, wandering bodies that were never planets at all. Mars is a world of ghosts. Its surface is a bone-dry desert, scarred by riverbeds that have been empty for billions of years and lakebeds that are now just dusty plains. It is a monument to a lost, wetter, and potentially habitable past. But the search for life there is not a search for the past alone. It is a hunt for something that may have retreated, gone into hiding, and perhaps even persists in the shadows of the present. Our rovers, like Perseverance, are robotic geologists slowly traversing the Jezero crater, an ancient lakebed. Their drills bite into the rust-colored regolith, not just to study rocks, but to collect pristine samples of a time when liquid water pooled on the surface. These core samples, sealed in tubes, are meant for a future, audacious mission to bring them back to Earth. Scientists like Dr. Jennifer Eigenbrod at NASA, a Goddard Space Flight Center, explain that our labs here have instruments far more sensitive than anything we can send on a rover. The hope is that within these Martian rocks, we might find biosignatures, chemical or structural fossils left behind by ancient microbial life. Yet the intrigue on Mars is not confined to ancient history. Orbiting spacecraft have spotted something peculiar, dark streaks that appear on sun-facing crater walls during the warmer Martian seasons, then fade when temperatures drop. These are the recurring slope lineae. The leading theory is that they are signs of briny water, salt saturated enough to remain liquid in the thin, cold Martian air, seeping just below the surface and darkening the soil as it flows. It is not a raging river but a damp trickle, a hint that liquid water, the essential ingredient, may still be active on Mars today. And where there is even the occasional presence of liquid water, the possibility of subsurface life, clinging to existence in damp cracks and pores deep underground, becomes a tangible, thrilling thought. This possibility is amplified by another atmospheric mystery, methane. On Earth, the vast majority of methane is produced by living organisms. On Mars, orbiters and rovers have detected sporadic, unexplained spikes of this gas in the atmosphere. It could be geological, produced by reactions between water and rock, but its transient nature makes scientists wonder, could it be biological, a faint exhalation from a deep, hidden microbial biosphere? The combination is compelling, a wet past preserved in stone, hints of present-day liquid, and a mysterious gas that whispers of activity. Mars teaches us that a habitable world can become a desert, and that life, if it ever arose, might not have vanished but simply gone underground, waiting in the deep, cold aquifers for a future discovery. This shifts our gaze from surfaces to subsurfaces, and ultimately, to worlds where the subsurface is not rock, but a global, sunless sea. Beneath the perpetual orange twilight of Saturn's largest moon, a world exists that holds a mirror to our own, but the reflection is made of ice and liquid gas. This is Titan, a place with river valleys, shorelines, and rolling dunes, yet its geology is sculpted not by water, but by liquid methane and ethane, flowing over a bedrock of water ice as hard as granite. It is the only other world in our solar system with stable liquids pooling on its surface, and it possesses a thick, hazy atmosphere of nitrogen, thicker even than Earth. This combination creates an environment of staggering complexity, where organic chemistry rains from the sky, coating the surface in a tarry sludge of hydrocarbons, the very building blocks of life as we know it. But here, the fundamental rules might be rewritten. Life on Earth is water-based, but on Titan, with its surface temperatures plunging to -290 degrees Fahrenheit, water is the rock and liquid methane is the solvent. Could life use a different liquid entirely? Scientists like Dr. Jonathan Lunine of Cornell University have proposed that hypothetical Teutonian microbes might breathe hydrogen gas and metabolize acetylene, a simple hydrocarbon abundant on the Moon's surface, for energy. It is a biology of profound alienness, operating on a timescale and with a chemistry we can barely fathom. The intrigue deepens with evidence from the Cassini mission, which suggested Titan also hides a global subsurface ocean of liquid water, sandwiched between layers of high-pressure ice. This makes Titan a dual habitable world, one with the potential for two separate, non-interacting biospheres, a water-based life in the deep ocean and a methane-based life on the frozen surface. To unravel these mysteries, NASA is preparing the Dragonfly mission. This ambitious project is not a rover, but a nuclear-powered rotorcraft, a drone designed to fly across Titan's dense atmosphere, landing at multiple sites to sample the organic-rich sands. Dragonfly will carry a suite of instruments to identify the complex chemistry of Titan's surface, looking for patterns that suggest prebiotic processes, or perhaps even the chemical fingerprints of a biology that does not rely on water. It is a search for life as we don't know it, in a landscape that feels both eerily familiar and profoundly other. Titan expands our imagination, proving that a habitable environment does not require a sunlit, temperate shore, but can exist in the deep freeze with rivers of hydrocarbon and a sky of perpetual orange dusk. It forces us to consider that the universe may be filled with life, not just on worlds like our own, but on those that operate by a completely different set of chemical rules. This realization sends our search outward beyond our solar system to the planets orbiting distant suns. The search for alien life must eventually leave our solar system behind, and the journey begins at our very doorstep, just over 4 light-years away. There, orbiting the small, dim red dwarf star Proxima Centauri, is a world known as Proxima b. It is an Earth-sized planet, and it sits within what astronomers call the habitable zone, the orbital sweet spot where temperatures might allow liquid water to exist on its surface. This discovery was monumental, placing a potentially habitable world practically next door in cosmic terms. But Proxima b is no second Earth. The reality of its environment is a lesson in cosmic extremes. Because Proxima Centauri is a faint star, the planet must huddle very close to it to stay warm, so close that it is almost certainly tidally locked. One side of the planet forever faces its sun, a land of perpetual, scorching daylight. The opposite side is locked in an eternal, frozen night. The only region where conditions might be temperate is the thin twilight line between these two brutal hemispheres. To make matters more challenging, red dwarf stars like Proxima are notoriously volatile, frequently erupting in massive stellar flares that would bathe any nearby planet in lethal levels of radiation, potentially stripping away its atmosphere over time. So, could life exist in such a place? The answer depends on 2 key factors: atmosphere and ocean. Scientists like Dr. Lisa Koltenegger at the Carl Sagan Institute explore the possibilities. If Proxima b has managed to retain a thick, global atmosphere, that air could act like a blanket, circulating heat from the hot day side to the frigid night side, potentially creating a band of survivable climate around the entire planet. Even more intriguing is the possibility of a global ocean. A planet-wide sea on a tidally locked world would create a powerful conveyor belt of currents, endlessly moving warm water from the sunlit side to cool and sink on the dark side, creating a stable, liquid environment across the globe. This ocean could also provide a protective layer, shielding any life beneath its waves from the harsh stellar radiation above. The importance of Proxima b extends far beyond this single world. Red dwarf stars make up about 75% of all stars in our galaxy. If a planet orbiting the closest one to us shows signs of habitability, It suggests the Milky Way could be filled with billions of such worlds. The next step is to look for proof. Future telescopes like the James Webb Space Telescope and its successors aim to do just that. By analyzing the starlight that filters through Proxima B's atmosphere during its transits, astronomers hope to detect the chemical fingerprints of gases like oxygen, methane, or an imbalance of gases that could only be explained by biological activity. Finding a biosignature here would be a discovery that reshapes our understanding of the universe, proving that life can take hold even in the challenging neighborhoods of the most common stars. This realization expands our search to a truly galactic scale, forcing us to consider that life may not even need a planet at all, but could exist in the vast, open space between the stars. Drifting through the eternal night between stars are entire worlds without a sun. These are rogue planets cast out from their birth systems by gravitational chaos to wander the galactic darkness alone. To picture one is to imagine the ultimate isolation, a frozen sphere adrift in a sea of nothingness, its surface temperature hovering just above absolute zero. Yet within this icy tomb, a profound warmth might persist. The heat from the planet's violent formation, or the slow decay of radioactive elements in its core, could still be radiating outward, trapped beneath a crust of ice many miles thick. This creates the possibility of a sealed, subsurface ocean, a pocket of liquid water kept warm by the planet's own internal heart, completely cut off from the universe. Astrophysicist Dr. David Stevenson has proposed that some of these nomad worlds could even retain thick atmospheres of hydrogen captured during their formation. This hydrogen would act as a phenomenal insulator, a cosmic blanket holding in that precious geothermal warmth for billions of years, long after the surface has frozen solid. In such an environment, the stage is set for a form of life we are beginning to understand. At the bottom of these lightless, pressure-crushing seas, hydrothermal vents could pepper the seafloor, just as they do on Earth. Around these vents, entire ecosystems could exist, sustained not by sunlight, but by chemosynthesis. Microbes would feed on the chemicals spewing from the planet's interior, forming the base of a food web that might include more complex organisms, all evolving in total isolation. The life here would know nothing of a sky, of stars, or of day and night. Its entire universe would be the dark water and the volcanic glow of the vents. The staggering implication is one of sheer numbers. Current estimates suggest there could be billions, even trillions, of these rogue planets wandering the Milky Way, far outnumbering the stars themselves. If even a tiny fraction of them possess these warm, hidden oceans, they could represent the most common habitable environments in the entire galaxy. They are dark, silent arcs, carrying the potential for life through the interstellar void, completely invisible to our telescopes. This forces us to expand our definition of a home. A world does not need to orbit a star to be alive. It only needs to hold onto its own inner fire. And if life can cling to existence in the absolute cold between stars, then perhaps it can also endure the opposite extreme, in the searing, violent embrace of a dying sun. Our galaxy may be filled with planets that have no land at all, only endless global oceans. These are the Hycean worlds, a class of planets several times more massive than Earth, wrapped in thick, steamy atmospheres of hydrogen and water vapor, and covered from pole to pole by a single, uninterrupted sea hundreds of kilometers deep. To stand on one would be to stand on the deck of a ship in the middle of a cosmic ocean with no shore in sight forever. The surface would be a warm, perpetually cloudy water world, but as you descend, the pressure builds to crushing extremes. So far down that the very nature of water itself changes, forming exotic, hot ices like Ice 7, where water molecules are squeezed into crystalline structures denser than liquid water, creating a bizarre, slushy barrier between the ocean above and the rocky core far below. For life, this presents a unique and challenging habitat. The absence of continents means no rivers wash minerals into the sea, potentially limiting the nutrients available in the upper, sunlit layers. Yet, research led by astronomers like Dr. Niku Madhusudhan suggests these worlds could be far more hospitable than we once thought. The thick hydrogen atmosphere acts as a powerful greenhouse blanket, trapping heat efficiently and potentially creating vast, temperate surface oceans even on planets orbiting far from their stars. More importantly, these atmospheres might be relatively easy for our next-generation telescopes to peer into. Scientists are particularly excited about searching for specific chemical signatures in the air of these worlds. One such molecule is dimethyl sulfide. On Earth, this gas is produced almost exclusively by marine phytoplankton, tiny living organisms in our oceans. If telescopes like the James Webb detect a persistent, unexplained abundance of dimethyl sulfide in the atmosphere of a Hycean world, it would be a powerful, indirect hint of a living ocean below. The life on such a planet would likely be microbial, floating in the upper layers where sunlight can penetrate, building its own ecosystem in a world without shores or seafloor vents. It forces us to reconsider the very recipe for a living planet. Land, it seems, may be optional. This expansion of the habitable zone to include these steamy, waterlogged globes dramatically increases the number of possible homes for life in our galaxy. And if life can begin in the deep time of a mature planet's ocean, it raises a profound new question. Could it also spark into being in the cosmic nursery itself, in the swirling disks of dust and gas where planets are born? The story of life may not begin on a planet at all, but in the vast, swirling nurseries where planets are born. Picture the infant solar system, over 4.5 billion years ago, not as a collection of worlds, but as a colossal, flat disk of gas and dust spinning around our newborn sun. Within this protoplanetary disk, temperatures ranged from searing heat near the center to unimaginable cold in the outer reaches, and in that gradient, something miraculous was happening on the tiniest of scales. Microscopic dust grains, coated in layers of water ice and simple carbon compounds, were drifting through the nebula. When these grains collided and stuck together, forming the first pebbles and then planetesimals, the complex chemistry of space itself was being baked into their very structure. Laboratory experiments and observations of similar disks around young stars today show that ultraviolet starlight and cosmic radiation can trigger reactions on these icy grains, forging complex organic molecules, even amino acids, the building blocks of proteins. This means the raw ingredients for life were likely present in the solar system's construction materials, written into the recipe from the very first moment. The evidence for this is quite literally falling from the sky. Certain meteorites, known as carbonaceous chondrites, are ancient relics from that primordial disk. When scientists crack them open, they find a rich inventory of organic compounds, including over 70 different amino acids. These are not signs of life itself, but proof that the universe's chemistry is predisposed to creating life's precursors in the cold dark of space. This discovery leads to a profound and ancient idea, panspermia. It is the concept that life, or its vital components, could travel between worlds, hitchhiking on comets and asteroids. A catastrophic impact on a young Mars, for instance, could have blasted rocky debris containing hardy microbes into space. After millions of years drifting in the void, a fragment of that Martian rock could have fallen to Earth, seeding our planet with life that originally began next door. This theory transforms life from a solitary accident into a potential galactic traveler. An even more speculative variation is directed panspermia, pondered by scientists like Francis Crick, who suggested an advanced civilization might deliberately send microbial life to promising young planets, perhaps as a way of spreading their biological legacy. While this remains in the realm of thought experiment, the core scientific insight is staggering. If the basic chemistry for life is a common product of star and planet formation, then the emergence of life may not be a rare miracle, but a regular, even expected phase in a planet's development. The universe could be subtly, consistently, and automatically biased toward biology. This cosmic perspective suggests that when we look out at the galaxy, we may not be searching for rare oases of life in a desert of dead rock. We might instead be looking at a field already sown with seeds, waiting only for the right conditions to make them sprout. And if life is indeed a natural outcome of universal chemistry, then around the oldest, most stable stars in the Milky Way, it has had the longest possible time to grow, evolve, and perhaps become aware of its own place in the cosmos. Our own sun is a relative newcomer in the galactic story. Billions of years before it even ignited, the first generation of stars had already lived and died, seeding the cosmos with the heavy elements that make rocky planets and life itself possible. Scattered throughout the Milky Way, especially in the ancient central bulge, are stars that are nearly as old as the universe itself. Their planets have had not just millions, but billions of extra years for the chemistry of life to begin, for evolution to work its slow magic, and for intelligence to emerge and gaze upward. This is the ultimate thought experiment in cosmic patience. If life arose on a world orbiting one of these elder suns, it could have had a head start of 3, 4, even 5 billion years on us. What might a civilization achieve with that unimaginable span of time? It is a duration so vast that it makes all of human history feel like the blink of an eye. In such a time frame, a species could master its planetary environment, its star system, and perhaps the very laws of physics. They might have long ago moved beyond biological forms, existing as patterns of energy or information, or engineered themselves into something we could not even recognize as life. This profound possibility leads directly to one of the great puzzles of modern science, the Fermi paradox. If the universe is so old and so vast, and life is at all common, then where is everybody? The silence is deafening, but there are many possible answers that do not require loneliness. Perhaps advanced civilizations practice a form of sustainable stealth, minimizing their cosmic footprint to avoid attracting attention in a potentially crowded galaxy. Maybe they have transcended into realms or dimensions we cannot perceive, leaving the physical universe behind like an outgrown shell. Or the simplest answer might be the sheer, overwhelming scale of both space and time. A civilization that flashed into existence for a mere 50,000 years, a geological instant, could have risen and fallen in the gap between two of our radio broadcasts, their signals now lost in the endless background noise of the cosmos. The distances between stars are so immense that a conversation could take centuries, making sustained contact a project spanning generations. Searching for these elder races, then, becomes an archaeology of both space and deep time. We might not find their broadcasts, but perhaps their artifacts, massive engineering projects like Dyson spheres that partially obscure their star's light, or probes sent out eons ago that now drift silently through the interstellar dark. This perspective reshapes the entire endeavor. We are not just scanning the sky for neighbors, we are sifting through the cosmic fossil record, looking for traces of intelligence that may have dawned when our world was still a cloud of dust. Having mapped these 10 potential havens from hidden oceans to ancient stars, we must now step back and ask the most human of questions. What would it truly mean if we found something? The discovery of even a single microbe on another world would forever change our understanding of the universe and our place within it. It would prove that the spark of life is not a singular accident on Earth, but a common feature of the cosmos. We would know with certainty that we are not alone in the grand story. That knowledge would humble us and unite us, transforming humanity from isolated inhabitants of a pale blue dot into conscious participants in a living, breathing galaxy. The search itself, this act of looking up and wondering, is a testament to our own awakening intelligence. Whether we find neighbors tomorrow or in 1,000 years, the journey to find them is already redefining who we are. The confirmation would arrive not with a shout, but as a quiet line of data on a scientist's screen, a pattern in a spectrum, or a microscopic shape in a rock sample. In that instant, a boundary in human thought would vanish forever. The discovery of life beyond Earth, whether a fossilized microbe in Martian clay or the chemical whisper of a forest in an exoplanet's air, would be the single most profound scientific revelation in history. It would prove that biology is not a lonely fluke on our pale blue dot, but a natural, repeatable process of the cosmos. We would know with certainty that we are part of a living universe. This knowledge would ripple through every facet of human culture, reshaping our philosophies and challenging ancient narratives about our special place in creation. It would forge a new planetary identity for humanity, uniting us not as citizens of nations, but as crewmates on a single spaceship Earth who have just learned the galaxy is teeming with neighbors. The scientific community is not waiting unprepared for this moment. Organizations like the International Academy of Astronautics have established detailed protocols for the verification and announcement of a potential discovery. The process would be meticulous, designed to avoid error or sensationalism. Any signal or finding would face relentless scrutiny, confirmed by multiple independent teams using different instruments before any public statement is made. The goal is to move from a thrilling possibility to an undeniable fact with the utmost care and transparency. Once confirmed, the real work begins, a quest that would define science for centuries. How does this alien biochemistry function? Does it use the same amino acids or a completely different set of molecular building blocks? Is its genetic code stored in something like DNA or in a molecule we have never conceived of? Understanding an independent genesis of life would give us a second data point, finally allowing us to see which principles of biology are universal laws and which are merely Earth-unique accidents. With such a monumental discovery comes profound responsibility, especially if the life we find is intelligent. The potential risks of haphazard communication are the subject of serious debate among scholars. Transmitting our location and nature into the cosmos without global consensus could be seen as naive, given we have no way of predicting the intentions or ethics of a civilization potentially millions of years more advanced than our own. This is why many researchers advocate for a period of intense observation and study first, a cosmic listening phase where we strive to understand before we announce ourselves. It underscores the critical need for international cooperation, moving beyond terrestrial conflicts to establish a unified, thoughtful approach as representatives of an entire planet. The search itself, then, becomes an exercise in maturity. It forces us to look outward with a blend of hope and humility, driven by curiosity but tempered by wisdom. This entire journey, from the hidden oceans of icy moons to the atmospheres of distant worlds, is ultimately a search for context. It is an attempt to answer the oldest questions: are we alone, and what does it mean to be alive in this vast cosmos? Whether the answer comes tomorrow or 1,000 years from now, the act of searching already transforms us. It pushes our technology, expands our imagination, and reminds us of the fragile beauty of our own world. The silence of the universe is not an empty void, but a canvas awaiting a first brushstroke. And with every telescope we point at the stars, every probe we send into the darkness, we are preparing ourselves for the day that canvas is no longer blank. From the dark abyssal seas of Europa to the acid-clouded skies of Venus, we have mapped a cosmos that refuses to be sterile. These 10 potential cosmic habitats, from wandering rogue planets to ancient stars, reveal a universe of staggering imagination, where life could cling to existence in ways that challenge our every assumption. This journey teaches us one profound lesson: life, if it is out there, will be defined by tenacity. It will be an expert at adaptation, finding a way in crushing darkness, in bitter cold, or in chemical soups we would consider poison. Its very foundations, the solvents it uses, and the energy it harnesses might be so alien that we could walk right past it without recognition. Yet this search for the strange and the tenacious is not just about finding others, it is about understanding ourselves and our place in the grand story. Every mission we design, every telescope we point at a distant sun, is an act of hope that pushes the boundaries of human knowledge and technology. It is curiosity made manifest, driving us to look deeper and think bigger. So tonight, when you look up at the stars, let that view feel different. See it not as a static tapestry of lights, but as a dynamic frontier, each point of light a potential sun with its own family of worlds, some of which may hold oceans, clouds, and perhaps a silent, waiting biology. The universe is a story still being written, and we are just beginning to read its pages. If this cosmic journey has sparked your sense of wonder, consider subscribing for more explorations into the mysteries of space. Let us know in the comments which of these potential homes for life you find most compelling, whether it is the icy plumes of Enceladus or the ancient silence around a primordial star. The greatest discovery in history still lies ahead, waiting just beyond the horizon of our current understanding.